Welcome to the Explainer. Today, we're doing something absolutely wild. We are going to act as your mathematical bridge, attempting to translate the highly abstract, discrete world of algebraic K-theory directly into the physical, macroscopic shape of the universe. It's a fascinating journey that connects the microscopic realm of pure numbers to the very fabric of reality itself. Here's our roadmap for today. We're going to hit the Birch-Tate identity, run through the Adelic translation pipeline, check out the p-adic interpolation kernel, warp the geometric boundary, and finally look at matter as arithmetic braiding. Let's go step by step from abstract algebra all the way to macroscopic mass. Part 1, the Birch-Tate identity. We're starting with the fundamental postulates connecting two seemingly unrelated math universes. Okay, take a look at this fundamental equation. It's literally the bedrock of our whole analysis. On the left side, we're tracking discrete quantum twists in the K-group. Think of them like tiny structural glitches or defects in spacetime. And on the right, those microscopic defects are perfectly balanced out by a continuous, smooth wave of vacuum energy, represented by the analytic zeta function evaluated at s equals -1. It's a brilliant picture of global information conservation, microscopic quantum chaos beautifully regulated by continuous global energy. Moving on to section 2, the Adelic translation pipeline. To actually get from that abstract identity to physical reality, we need a mathematical translation mechanism. Think of this pipeline like a massive mathematical manufacturing plant. It relies on three main mechanical steps to process our data stream: the GRR pushforward, the zeta K deformation, and finally, global functional equation integration. So if you follow the data flow from the top down, we kick off with abstract K-group torsion elements. That data filters down through the GRR pushforward to grab our local indices, passes through the zeta K deformation to create a new geometric representation, and then drops into the global integration at the bottom. This whole process is what rigorously yields the core identity match, verifying our initial Birch-Tate ratio. Now, here's the precise source equation driving that first big transformation. By tracking Gauss cohomology, this mathematical operation grabs those abstract disconnected K-group points and lifts them into a full multidimensional matrix representation. The really vital takeaway here? The sheer size of that initial abstract torsion group directly dictates our output. It defines the local conductors and physical limits across finite primes. Check out the exact structural bridge in this center equation. You've got high-energy spectral weight on the left and deep arithmetic core on the right. The left side is computing the continuous macroscopic volume of our space, while the right isolates the tiny, discrete arithmetic data. And because the underlying math is based on totally real numbers, a global lock guarantees perfect reflection symmetry across that mirror axis. The continuous volume absolutely has to match the discrete data. All right, section 3. The p-adic interpolation kernel. To handle the cyclical jumps in our arithmetic data packets, we've got to introduce a dynamic filter. Before we hit the next equation, it's super important to understand the p-adic L function. You can really think of this as a mathematical smooth operator. It acts as an analytic interpolation kernel. Basically, it takes completely isolated, disconnected data points and weaves them together into a continuous flowing wave field, smoothing out all those harsh, discrete cyclotomic jumps. Take a close look at how the core arithmetic value gets multiplied by that term in the parentheses on the right. Subtracting that local factor acts as a built-in safety net and natural UV cutoff. It systematically strips away localized quantum self-energies, which regularizes the mass and stops our physical values from just blowing up to infinity. And here is the Iwasawa Main Conjecture identity in action. On the left side, we have a discrete arithmetic code block, and on the right, our continuous, smooth operator. This identity proves they're describing the exact same density of information. But what's really amazing is that when we evaluate this exact structural identity at the physical stability boundary of s equals -1, it snaps perfectly back to recover our initial Birch-Tate equality. It's like a giant puzzle coming together. Moving to part 4, warping the geometric boundary. Now we need to stress test our mathematical framework by throwing a wrench in the works, shifting from a flat, totally real field to an imaginary quadratic field. This shift creates a massive algebraic shock to the system. By mapping directly to the complex plane, we force a 0 of order 1 into our partition function. You can actually see it right there where the zeta function evaluates to 0. And because of this sudden 0, our entire classical discrete baseline just collapses entirely. Suddenly, the local data packets have absolutely nothing solid to anchor to. So what happens? It triggers a dramatic topological shift. In the totally real field we were just looking at, we had flat geometry and stable data. But with this new imaginary field, our stable zero vanishes. To survive, the data stream has to violently decompress its energy budget, stretching from analog flat spacetime sheets into a curved, sweeping hyperbolic geometry. When you compare these two realities side by side, the crucial point becomes clear. When that stable integer base drops out to zero, Bloch's conjecture steps in, kind of like an emergency backup generator. It uses its transcendental regulator to stabilize the universe. The structural information doesn't just disappear, it decompresses out of those discrete points and expands right into continuous, curved spaces. So how does this warping actually calculate out? Enter the Bloch-warped boundary identity. By pushing the limit as s approaches -1, the emergent 4D cosmological constants of our universe lock into this new global hyperbolic volume. Driven by that complex Wigner-Bloch dilogarithm function tracking complex singularities on the far right, the cosmological constant basically transforms into a dynamic, shifting field. Finally, Section 5, Matter as Arithmetic Braiding. This is the physical payoff of our tutorial, where we actually derive the macroscopic stress-energy tensor straight from these algebraic relations. First up, let's look at the basic generators of our theory, the Steinberg symbols A and B on the left. Watch how these discrete arithmetic data packets are processed. Lifted via the GRR pushforward, they map into the one-form regulator on the right. This transforms them into a physical measurement of how the data stream literally twists and mismatches around internal geometric fibers. Now, when the Fourier-Mukai kernel processes this phase form, that internal twisting creates a spark, a highly localized microscopic current. Notice the internal fiber coordinates swirling on the left side, which are perfectly defined by the Kern equation over on the right. That deep internal arithmetic twist, that is the exact microscopic engine sourcing stress energy. And here is the ultimate mapping. This operator equation is an absolute masterstroke. It takes those purely abstract math symbols and projects them directly into our continuous, macroscopic 4D universe as the stress-energy tensor. On the left side of the equation, we get energy density, the literal mass shadow. And on the right, because our symbols are naturally antisymmetric, they project outward as localized Einstein-Cartan spacetime torsion. We are literally watching math become matter and gravity. So why does all this matter? Well, this math tutorial yields 3 profound architectural truths about our reality. First, the illusion of substance. Matter isn't just stuff sitting in an empty box. It's a localized region of rationally braided information. Second, the origin of the mass gap. Mass is globally quantized and strictly regularized by a global function, preventing infinitely small fractions of energy. And third, the quantization of spacetime torsion. Continuous flow suppresses these twists at low energies, keeping the macroscopic spacetime we actually observe beautifully smooth. I want to leave you with one final provocative thought to wrap up this explainer. If the physical matter of our macroscopic universe is merely rationally braided arithmetic data, what other hidden topological structures remain undiscovered in the mathematics of primes? As you digest the equations we've looked at today, just let that sink in. Hopefully, it sparks your curiosity to dive even deeper into the Adelic Langlands Program. Thanks so much for exploring this with me.